Light waves. Light waves travel through space in straight line and will continue to do so unless diverted from its original position. A change in direction takes place when light strikes and rebounds from a surface. So, what is reflection? Reflection from very smooth mirror surfaces is called reflection or regular reflection. In spectacular reflection incident parallel, rays are parallel and the reflection in contrast. Rays reflected from relatively rough surfaces are not parallel but scattered. Refraction. When light strikes in transparent medium, some light is reflected and some is transmitted. This transmission is illustrated for a beam of light incident on the surface of the body of water. Upon investigation, you will find that the transmitted light has changed direction in going from medium to another. Light has changed direction in going to from its original path arises because of its change in the speed of second medium.
Reflection and dispersion. This is a phenomenon on which light changes in direction of travel when it strikes between the interfaces of the two different media. Dispersion. Dispersion is a splitting of light into its seven constituent color, either violet, indigo, blue, green, orange, and red. So reflection. Reflection takes place when the light does not pass into the material, but instead bounce off the surface. Refraction occurs when the light passes into the material, and dispersion of light is through a prism with all seven colors is separated of emerging of the ray. Refraction in action. A beam of light is reflected. That is, its direction is change of entering the water. Speed of the different medias expressed in terms of a ratio relative to a speed of light. This is known as the index of refraction. And the speed of light in the direction in the water is this. Is the example of flashing light into a water. So the index of refraction equals the speed of light in a vacuum over the speed of light in a medium. Or this one. N equals C over Cm. The index of refraction is a pure number. It has no units because C and Cm are measured in the same units, which cancel. The index of refraction of some common substance are given in the table 7.1. Kani nga table? Kani. This table. Note, the index of refraction for air is close to the for vacuum when light passes obliquely. Open parenthesis 0 and 0 degree ba? Tas kanis masa, ano siya? Ano siya? Into a denser medium, for example, from air into water or glass dash light, rays are refracted or bent towards the normal ani open parenthesis 0 klaro. It is slowing of light that causes the deviation. Complex processes are involved, but instinctively we might for example, the speed of light in a water about 75% its speeds in air or vacuum. As shown in the following are the example. So example 7.1, finding the speed of light in a medium. This is the picture. So what is the speed of light in a water? Thinking it through. The speed of light in a medium over this one is expressed by the index of refraction in terms of a ratio to a relative of light in a vacuum. N equals C over Cm. In this case, the medium is water. So solution, this one. Given nothing directly with, therefore quantities are known or available from tables. Step 2, wanted speed of light in a medium, open parenthesis, water, close. This value may be found from EQ 0.71. The speed of light is known. C is equals to 3.00x 10 over 8 ms m over s. And so this is the index of refraction of some common substance. Substance is equals to N. Water is equals to 1.33. Crown glass is equals to 1.52. Diamond is equals to 2.42. Air is equals to 1.00029. Vacuum is equals to 1.00000. And now for the refraction analogy. So this is the example of refraction analogy. Marching obliquely into a muddy field causes for a brand columns to change direction. The confidence or frequency remains the same, but the marches in the mud slips and travel shorter distance for a shorter wavelength. This is analogous refraction of a wave front B. So ano siya? Kani. Next is the refraction and dispersion. Refraction and dispersion are these examples. Ano siya? Then refraction of mirages. A wet spot mirage is produced when a light from the sky reflected by warm in near of the road surface. The index of refraction with the temperature. Then other things are optics and waves effect. So from the example of optics and wave effect, sunset from the observer horizon, then apparent sun, then actual sun. Reflection nga pa niya. Then refraction effects. The sun appears flattened because the light from the top and bottom portion is reflected as is passed through the different atmospheric densities near the horizon. So meron siya kanang ang half niya nakita niya, then mato siya maraming naka-spread kay pado naman siya mo low, sa siya mo low tanan. So reflection by refraction, when light goes from denser medium into a less dense medium, for example from the water of glass into air. Ano siya man example niya? And internal refraction, when light goes from a denser medium into a less dense into air, as illustrated here, it is refracted away from the normal at a certain critical rate angle. The angle of the refraction is 90 degrees for incidence greater than the critical angles the light reflected eternally. Refraction and dispersion. Refraction and internal reflection. A beam lights travel in a piece of glass is eternally reflected. Some of lights is transmitted at the reflecting surface. So for example is diamond. So mga siya ang diamond. Ano siya? Ano siya mga examples sa kaning refraction and dispersion. Optics and waves kani siya mga gapon siya example sa dispersion. So in this time ako mahatag lang og kana mga samples, then after this video na kay presentation from YouTube, then mana siya mas naka-explain more than sa ako. So this is the line spectra. Kana siya nga mga samples, line spectra na siya. Then the rainbow of dispersion and internal reflection kani siya. Ani. From the eyesight, then rainbow formations, rainbow formations. So that's all for today, and watch the video after this video. Thank you and have a good day.
Bend when it passes from one medium into another. And this picture really shows the refraction of light. You can see this glass rod is bent at the interface between air and water. So here we have the interface between air and water, and this vertical dashed line that I'm drawing represents the normal line. The normal line is perpendicular to the interface between air and water. It's at a 90-degree angle. Now, when the light ray strikes the point of incidence, three things can happen. The light ray can reflect at the boundary, it can refract, or it could be absorbed by the material. This is known as the incident ray. This is the reflected ray. And the one on the bottom is the refracted ray. The angle of incidence is the angle between the incident ray and the normal line. So let's say that's 45 degrees. According to the law of reflection, the angle of incidence is the same as the angle of refraction. So these two angles must be equal to each other. Now my drawing is not precise, so it may not look like they're the same, but they should be the same. Now this angle here is known as the refracted angle. And in order for us to calculate that, we need to use something called Snell's law, also known as the law of refraction. And it's n1 times sine theta 1, which is equal to n2 times sine theta 2. So that's Snell's law. It can help us to calculate the angle of refraction or the index of refraction. The index of refraction for air is approximately 1. For a pure vacuum where there's no molecules in the air, it's exactly 1. The index of refraction for water is 1.33. So with this information, we can calculate the angle of refraction. So n1 we're going to say is 1 and n2 is going to be 1.33. So it's 1 times sine 45, and that's equal to 1.33 times sine theta 2. Sine 45, that's equal to the square root of 2 divided by 2, which as a decimal is 0.7071. If we divide that by 1.33, we'll get that 0.53166 is equal to sine of the second angle. Now, in order to calculate that angle, we need to use the arc sine or the inverse sine function. And that will give us theta 2, which is the angle of refraction. So if you type in an arc sine 0.53166, it'll give you an angle of 32.1 degrees. So that is the angle of refraction. So notice that as the incident ray moves from a material with a low index of refraction to a material with a higher index of refraction, the ray bends closer to the normal line. The angle decreased from 45 to 32.1. Now the reverse is true. If the incident ray traveled from a material with a high index of refraction to a material with a low index of refraction, the angle is going to increase. And so it's going to bend away from the normal line as opposed to toward the normal line. Now, another interesting fact that you want to know for this topic is the speed of light. The speed of light is not always 3 times 10 to the 8 meters per second. In fact, it changes based on the material that it is traveling in. This is the speed of light in a vacuum. The speed at which light moves depends on the material it's moving in. And here's how you can calculate the speed. The speed is equal to the speed of light divided by the index of refraction. So the speed of light in air is going to be 3 times 10 to the 8 meters per second divided by 1, which is 3 times 10 to the 8 meters per second. Now what about in water? How fast does light travel in water? Well, we can calculate that using the same formula. So it's going to be V is equal to C over N. So C is not going to change. That's going to be 3 times 10 to the 8 meters per second. If we divide it by 1.33, which is the index of refraction of water, we can get the speed of light in water. And so in water, light travels at 2.256 times 10 to the 8 meters per second. So notice the relationship between the speed of light and the index of refraction. When light travels in a material with a high index of refraction, the speed decreases. So diamond, for example, has a very high index of refraction. If my memory hasn't failed me, I believe it's around 2.4. So light travels very slowly in diamond, but it travels a lot faster in water or air compared to diamond. So far, we've considered the example where light travels from a material with a low index of refraction to a material with a high index of refraction. And we saw that the light bent closer to the normal line. Now let's consider the other situation. Let's say we have glass on the bottom, air on top. The index of refraction for glass is 1.5. There's different types of glass out there, but for the most part, it's close to 1.5. So this is going to be the incident ray. And this time, the refracted ray is going to move away from the normal line. Let me make this angle smaller. So I'm going to choose an angle of 40 degrees. So that is the angle of incidence. Now let's calculate the refracted angle. So it's N1 sine theta 1, which is equal to N2 sine theta 2. So N1, we're going to say that's for glass. That's 1.5 times sine of 40 degrees. That's equal to N2, the index of refraction for air, times sine theta 2, or theta r for the angle of refraction. So 1.5 times sine 40 is 0.96418. So the refracted angle is going to equal arc sine of 0.96418. So the refracted angle is 74.6 degrees. So when light moves from a high, let me say that again. When light moves from a material with a high index of refraction to a material with a low index of refraction, the light ray bends away from the normal line. Now there's something interesting that's about to happen here. notice what's going to happen if we increase the angle of incidence. If we increase it, the ray is going to bend even further. At some point, the ray will travel in between the interface of air and glass. And if we increase that angle even further, something called total internal reflection will occur, where all of the light rays will reflect and none of it will be refracted. But before total internal reflection occurs, there's something called the critical angle, which the angle of refraction is equal to 90 degrees. That's when the light ray is between the two boundaries, as represented by the ray in red here. Let's calculate that critical angle. So once again, we could use Snell's law. So N1 is going to be 1.5 times sine. The instant angle is the critical angle. N2 is 1. The instant angle is the critical angle when the refracted angle is equal to 90 degrees. So sine 90 is 1. So we have 1 divided by 1.5. And that's equal to 0.6 repeated. So the critical angle is going to equal arc sine 0.6 repeated, or 2/3. So in this example, the critical angle is 41.8 degrees. If you choose an angle that's greater than this number, total internal reflection will occur. But if you make the incident angle equal to the critical angle, then the refracted ray will travel along the boundary between air and glass, which is an interesting phenomenon to see. So that's basically it for this video. Hopefully it improves